Let's see how we deal with the radiation heat transfer when there are more than two surfaces. Let's say we have an enclosure with the three surfaces here. Surface 1, A1, with the emissivity of epsilon 1, T1, A2, epsilon 2, T2, and this is surface 3, A3, epsilon 3, and T3. And let's say this closure consists of all the surfaces, these three surfaces. There are three, okay, and diffuse, and gray surfaces. Now, if I just start from each of these surfaces and draw the resistance to the heat transfer, let's say for surface 1, we're starting from point EB1. Then we have the surface resistance, which is R1, 1 minus epsilon 1, A1. Then we reach to the point J1. Now this surface has radiation heat transfer between the other two surfaces too. So there are one between J1 and J2, which comes from surface 2, and there is this space resistance R12, which is 1 over F12 A1, and there is another one between J1 and J3, which is surface 3 with the space resistance of R13, which is 1 over F13 A1. The same thing between J2 and surface 2. This is the surface resistance R2, which is 1 epsilon 2 A2. This is EB2, and there is a transfer of radiation between J2 and J3 with the space resistance of R23, which is 1 over F23 A2. And here there is this surface resistance R3, which is 1 minus epsilon 3 A3. And here we have EB3. Now, in terms of the heat transfer, we have Q1 here, Q2 here, and Q3 here. Now, Q1 that is transferring through this surface resistance and reaching to the point J1, it has two parts, Q12 and Q23. The same thing, this Q2 that is coming, part of that just goes here, Q23. I don't write Q21, which is equal to minus 1, 2 here. Now, knowing the temperature, if we know the temperature, then EB1, EB2, and EB3 are known. They are sigma times T to the power of 4. If we want to find out the let's say Q1, we need to find out in addition to the EB1, 2, 3, we need to have the radiosity. So we need to find these nodes J1, J2, and J3 to determine the net radiation heat transfer from each surface. And the net heat transfer from each surface, remember that Qi was the summation of J equal to 1 to N Qij, which is the summation of J 1 to A, Ai, Fij, Ji minus Jj. In terms of the resistance, J1 to N, Ji minus Jj divided by Rij. Okay. So what this tells us is essentially Q1 is going to be Q12 plus Q13. That's what it tells us. Now, to find out the J1, J2, and J3, what what we can see here is we can look at each of these nodes, J1, J2, and J3. And each of these nodes, what we can write is the balance of the radiation energy. Q1 just gets in, part of that goes here, part of that goes here. So I can write that one here at each node. The net radiation should be 0. So Q1 is equal to Q12 plus Q13. Or if I just replace that, Q1 is EB1 minus J1 over R1. Q12 is J1 minus J2 over R12 plus J1 minus J3 R13. The same thing, Q2 is Q21 plus Q23. EB2 minus J2 R2, J2 minus J1 R21. R21 is equal to R12. So I'm just going to stick to that, plus J2 minus J3 R23. And the same thing here, Q3 is Q31, Q32, EB3 minus J3 divided by I3 equal to J3 minus J1 R13 plus J3 minus J2 R23. Now, having these equations, having all the resistance here, what we can do is there are 3 equations, 3 unknown, J1, J2, and 3. We can find each of them, and then from there, when we find it, we can find what is the QI. So a couple of things here is I was just writing, let's say here, instead of 2, 1, I was writing 1, 2, and that's the fact that called F12A1 is F21A2. So 1 over F12A1 is equal to 1 over F21A2, or R12 is equal to R21. And the same thing, Q12 is minus Q21. So keep these in mind. And next, I'm going to look at an example for a similar problem.